Hello! In this video, we're going to prove the following theorem. Suppose R is a relation from A to B. Then, the inverse of R is equal to R. Now, first, I would like to mention that R and R inverse are both relations from A to B. And see why that's true. First of all, we're given that R is a relation from A to B, which is equivalent to saying that R is a subset of A times B. Next, if we take the inverse of R, then that will just swap A and B around, and we'll have that R inverse is a relation from B to A. And if we take the inverse yet again, that'll swap B and A around, and we'll get that R inverse is a relation from A to B. So as you can see, both R and R inverse are relations from A to B. Okay, but why is this important to mention? Well, take a look at the statement we're trying to prove. We're trying to prove that two sets are equal. And this statement is equivalent to saying that for all objects P, we have that P is an element of this set if and only if P is an element of this set. So really, this is the statement we're trying to prove. But wait a minute, where are we getting our objects P from? Well, remember, we mentioned that R and R inverse are both relations from A to B. In other words, both R and R inverse are subsets of the set A times B. Therefore, we can think of our objects P as though we're pulling them from the larger set A times B. So really, this is the statement we're trying to prove. Now, we're trying to prove a statement involving all elements of A times B, so let's consider an arbitrary element of A times B. And every element of A times B is an ordered pair, so let's say our arbitrary element is the ordered pair A comma B. Now, we want to show that A comma B is an element of R if and only if A comma B is an element of R inverse. And we're going to do that by establishing a chain of if and only ifs. And to do so, let's start by writing that A comma B is an element of R if and only if. If and only if what? Well, if we recall from the definition of the inverse of a relation, this statement is equivalent to if we instead swap the order of A and B and say that B comma A is an element of the inverse of R. And applying that same idea yet again, this statement is equivalent to if we swap the order of B and A, and we say that A comma B is an element of the inverse of R inverse. So now we have a chain of if and only ifs showing that A comma B is an element of R if and only if A comma B is an element of R inverse. And since A comma B was an arbitrary element of A times B, this means it's true for every element in A times B. So we have proven precisely this statement. And therefore, that amounts to proving that R is equal to R inverse. And so this completes the proof. And so yeah, that's pretty much the idea of how you could prove something like this. So yeah, that's pretty much it for this video.